Hello, today we are presenting our project Implementation of Space-Time Block Codes in Cooperative Communication System. It is submitted by batch C13 under the guidance of Ms. B. Tulsi Saujanya. Multiple input, multiple output systems are the antenna systems wherein multiple antennas are put to use at transmitter section and the receiver section. Spatial multiplexing and space-time block coding are MIMO-based techniques that provide link quality and high magnitude in the system. Spatial multiplexing and space-time block coding can be combined to give a transmission scheme that will give a maximum average data rate over the MIMO systems. Though MIMO has advantages over other systems, the use of multiple antennas at the transmitting and receiving side occupies humongous space and consumes high power. Thus, the concept of cooperative communication is employed. Recently, from industrial and academic point of view, the concept of cooperative communication and wireless communication networks has drawn considerable attention as it can be used in addressing the performance limits of wireless communication networks because of customer mobility and storage of network resources. Cooperative communication enables effective utilization of communication resources by allowing nodes or terminals in a communication network to collaborate with each other in information transmission. It is a promising technique for future communication systems. Cooperative communication can significantly improve the system's spectrum efficiency and performance. MIMO exploits multiple paths rather than moderating it, and space-time block codes is a special form of Almaty code wherein two transmit antennas and one receive antenna are originally employed under flat fading circumstances. In this project, effective transmission is forged using space-time block codes in cooperative communication systems with full diversity. Coming to the multiple antenna systems are classified based on the number of antennas employed at both the receiver and transmitting side of the wireless communication. So they are categorized into four different types: CISO, MISO, SIMO and MIMO. In CISO system, there is one transmitting antenna and one receiving antenna. In SIMO, one transmitting and M receiving antennas. In MISO system, there are N transmitting and one receiving antenna, whereas in MIMO systems, N transmitting and M receiving antennas are there, wherein the number of transmitting antennas are always less than or equal to the number of receiving antennas. The performance of these systems are calculated by using one of the parameters called BER, which is always compared with the SNR, which is signal to noise ratio. BER, that is bit error rate, as the name implies, is defined as the rate at which errors occur in the transmission system. So BER can be given as errors by total number of bits. It can be directly translated into the number of errors that occur in a string of a stated number of bits. The main reasons for the degradation of a data channel and the corresponding bit error rate BER is noise and channel and changes of propagation path. BER is calculated as a Q function of root SNR. In a CISO system, BER is calculated as Q function of root h square, mod h square into SNR, and in BER and in SIMO case, BER is calculated as Q function of root norm of h square into SNR, wherein h are the fading channel coefficients. As we can see from the graph, which is plotted as BER versus SNR versus BER for both CISO and SIMO cases, we can see that in case of SIMO, the rate at which the BER falls with respect to SNR is much more when compared to the CISO case. When we simply consider the BER at the point SNR equal to 30 dB, in CISO case the BER is equal to 4.717 into 10 power minus 6, whereas in case of SIMO it's 1.833 into 10 power minus 39. So from the stats we can see that at one point of SNR, the BER of the SIMO case is always less when compared to the CISO. Thus, from this we can conclude that with the increase in the number of antennas, the BER falls rapidly. Hence, we employ MIMO systems. The path from the transmitter to receiver is not smooth, and transmitting delays may go through and the transmitting signal may go through various kind of attenuations, including path loss, multipath attenuation, etc. The signal attenuation throughout the path depends on various factors, and so fading is nothing but the time variation of the received signal power due to changes in transmission medium. And fading depends on various factors, as we have said beforehand, like path loss and multipath attenuation. So there are several types of fading, and fading are broadly classified into large scale and small scale fading. And in small scale fading, it is further divided as multipath delay spread and Doppler delay spread fading. In Doppler delay spread, there are two important things called fast fading and slow fading, wherein we're considering slow fading, we're considering our channels to be slow fading in the project. So slow fading is nothing but the result of shadowing by buildings, hills, mountains, and other objects over the path. Here the Doppler spread is quite low, and the symbol period is much less when compared to the coherence time, and signal variation is greater than the channel variation. The slow fading results in a loss of SNR, and to overcome the fading present in the system, we go to diversity techniques. Diversity is a powerful communication receiver technique that provides wireless link improvement at relatively low cost. Diversity techniques are used in wireless communication system to primarily improve the performance over a fading radio channel. So instead of the whole concept of the diversity techniques is that when transmitting so the whole concept of diversity is that instead of transmitting just one copy from the transmitter to the receiver, we take L copies of the signal which is to be transmitted, and it is transmitted over M channels. Diversity techniques are broadly classified into four types, which is time diversity, frequency diversity, polarization diversity, and spatial or antenna diversity. In time diversity, the antennas different antennas are allotted different time slots, and in frequency diversity, different antenna systems are allotted different frequencies to receive. In polarization diversity, all the different antennas employed have different polarizations, and in spatial or antenna diversity, the antennas are physically separated by a space. In our project, we are considering spatial or antenna diversity, since in MIMO case, all the multiple antennas employed in both receiver as well as transmitter side are multiple. Coming to cooperative communication, the reason why we are going to cooperative communication, as I mentioned beforehand, is that while using MIMO systems, the receiver and transmitter side have multiple antennas, and because of employing multiple antennas, the space occupied by these antennas is quite high, and also power consumed is high. Hence, we go to the concept called cooperative communication. In cooperative communication, the main thing which happens in the cooperative communication is sharing of resources. So and the users using the resources will not just restrict themselves to one particular resource, but they'll be sharing all the different resources, which is much more effective when compared to the MIMO system. And in our project, we are implementing this cooperation technique based on a model called relay channel model. In this model, a number of relays are employed between the source and destination, wherein the source transmits the signal and the destination receives the signal. And these resources, whatever are being shared, they are shared in such a way that a full diversity has been achieved. Full diversity as in all the antennas employed are transmitting it perfectly. The relay model employed in this project has been shown in this figure, where this model is specifically called a two-hop relay model, wherein there are just two hops as shown in the figure, source to relays and relays to destination. The F1, F2 and FR, all you can see on the part 1 of the cooperative communication, are the channel gains between the source and the relays. And G1, G2, G3 as seen in the part 2 are nothing but the channel gains from the relays to the destination. Now coming to the part 1 of the cooperative communication, source will be transmitting the signals to the relays. Here, the signals whatever have been transmitted are nothing but t-length vectors, that is root p1 ts, which in turn will be received by the relays. As shown in the figure, f1s are the channel path gains of the ith relay. Now the received vector which the ith relay receives is Ri, which is equals to Fi into root of P1 Ts plus Vi, where F1 as mentioned is channel path gain. Root P1 Ts is the t-length vector, where P1 T is the average transmit power, and Vi being the noise of the channel from source to the ith relay, and this Vi has zero mean and unit variance. Coming to the cooperative communication of the part 2, wherein the relays will be transmitting the signals to the destination. We consider all the relays to be transmitting simultaneously, as they're synchronized at a bit level, and there'll be a matrix, a T by T unitary matrix called AJ, which is relay matrix, which will be wherein all the relays will be equipped with these relay matrices. So the jth relay, which transmits the t-length vector tj, is actually a function of rj. The tj can be written as root p2 by p1 plus 1 ajrj, or tj equals to root p2 by p1 plus 1 ajrj bar, wherein rj bar is the complex conjugate of the rj vector. We consider that 1 to n relays will be transmitting Rj, and n to r relay, n plus 1 to r relays will be transmitting Rj bar. And throughout our project, the assumption which we take is this half n equals to r by 2. That is, half of the first half of the relays transmit Rj, and the second half will be transmitting Rj bar. Now finally, output as the destination is calculated as y equals to root p1 by p1 plus p2 by p1 plus 1, and summation from j equals to 1 to n, that is first n relays transmitting gj into ajrj plus summation n plus 1 to r, wherein n plus 1 to r relays transmit gj ajrj bar, which is further simplified as P1 P2 T by P1 plus 1 sh plus V plus W.